Welcome back to the Gas Compression Podcast. I am joined again uh, with Jim Dettore from FAS, that's Failure Analysis Services Training. And Jim goes all over the country and trains, equips, and teaches about what to look for in gas compression applications for failure, how to prevent it, what to do when you see it, how to diagnose it, all that good stuff. And so we're doing a four-part series. And last week we started talking about wear and abrasive wear. And this week we're talking about adhesive wear. So Jim, welcome back.
Thanks, Michael. Good to be back.
Yeah. So well, you want to fire up your PowerPoint or you want to give us a little intro?
So I'll start with a little intro, just kind of recapping a little of what we covered last week with the abrasive wear. And one thing I'm not sure if I mentioned last week was when we get into abrasive wear situations, identifying what the abrasive contaminant is very, very important. So I'll just preface with that. And then this week I thought we'd talk about adhesive wear, which is something that abrasive wear can very quickly progress to. And abrasive wear is the most common wear type that we see. Adhesive wear is when we start getting metal to metal contact, usually in a sliding action, metal to metal contact, and surfaces reach very, very high temperatures very, very quickly, especially if lubricant isn't present. So
Mhm.
this can happen with or without lubrication. Just want to be sure the listeners understand that. But when we start talking about adhesive wear, some people in the industry refer to it as wiping when we apply that to compressor bearings and engine bearings, wiping the bearing. And it's the same terminology, or a little different terminology, but the same meaning, which the wiping is also adhesive wear, basically getting metal to metal contact. And I put together a little presentation that I thought that we could go through that might be helpful for the listeners and the viewers.
Mhm.
And I can go ahead and kick that off if you like,
Yeah.
and we'll talk about it. Okay, here we go. All right. So as we start talking about adhesive wear, we'll roll through a few different slide pictures, which are basically just examples of what different types of adhesive wear might look like on various components, right? So when we talk about adhesive wear, and last week, Mike, we talked about two-body abrasive wear, right? And
Hmm.
two-body abrasive wear was when these asperity or surface peaks come in contact with the opposite surface in a sliding operation, and it starts to just cause very slight point contact tip wear. We referred to that as two-body abrasive wear. This week we're going to talk about adhesive wear, and when it happens, what's happening is these asperities or surface peaks are coming into contact with one another, and then they start to flatten out or bend over or shear off, and we start to get flat surfaces, and these surfaces start to rub together and generate frictional heat. As we generate this frictional heat, surface temperatures are often reaching melting temperatures very, very quickly, sometimes within a matter of seconds, depending on the speed or the load of the part, right? So when we start reaching melting temperatures on the surface, then we start to transfer material potentially from one surface to the other. Oftentimes, it's the material that has the lower melting point that will deposit on the surface of the material that has a higher melting point. So essentially, if we wipe or we generate adhesive where in a crankshaft bearing, the crankshaft is much harder than the bearing, so the bearing material wears away and deposits itself on the crankshaft, and then also a lot of that material flows out with the oil flow as it's released and into the sump or into the filter. So that's kind of how adhesive wear happens is we're generating considerable frictional heat between sliding surfaces. And this can happen with or without lubrication. Other things that tend to create it, and I'll just run through a list here right quick, things that can cause adhesive wear. If we have incorrect clearances or incorrect tolerances, if parts are too tight, and we start to get thermal expansion or thermal growth as parts begin to warm up during operation, then we get the metal to metal contact. The lubricant isn't going to be able to maintain a film between those pieces simply because the clearances are too tight and we're getting the metal to metal adhesive wear happening. Another thing that can happen is we can have excessive load that can potentially overcome the lubricant's ability to keep those surfaces separated. We really want everything to ride on a film of oil,
Mhm.
right? Especially in a sliding operation. So sometimes with load, we can overcome that. Sometimes at initial startup, we haven't generated oil flows. And if we start to put load too soon before oil flow has generated and oil films have developed between surfaces, then adhesive wear can start very quickly in that case as well. Another possibility is that when we have the abrasive wear, if you recall last week, Michael, we talked about some of those particles plow through a surface, like a soft bearing surface. And as it plows through that surface, it raises edges or berms on either side of the cut or the groove that it's creating. When this happens, effectively those raised edges progress to adhesive wear very quickly because they reduce the clearance. Does that make sense?
Oh yeah.
Okay, so the abrasive wear can progress to the adhesive wear as well. When we see adhesive wear occurring, sometimes it causes failure, sometimes it's catastrophic. Other times it is a very small point where it's created an issue, but then either the load has been released or sufficient lubricant has been supplied to keep the surfaces either lubricated or cooled. And sometimes we'll just see small areas that have some adhesive or wiping damage, but it didn't lead to catastrophic failure. We'll see that when we tear it down, or sometimes when we roll bearings into a unit that experienced intermittent adhesive wear, we'll see where it had bonded a little bit of the bearing material to the crankshaft and damaged the bearing, but continued to run, right? So it doesn't always lead to catastrophic failure, but it can. And I've got some good images of what it looks like, and we'll just go ahead and continue with those. So here we've got a set of G3500 engine bearings. And as you can see, the bearing on the left is black and heavily disfigured, a lot of what we call plastic deformation. It got so hot that the metal became plastic and was actually able to reshape and reform itself, right? So here we've got severe adhesive wear. Now this bearing here, and let me back up, these are main bearings that are supporting the crankshaft. These uppers in this case here are actually the lower main bearing that are receiving all the load. And these are the upper main bearing that the oil is coming through this hole here and traveling through this groove here to get to these bearings.
Mhm.
So what's happening here is this bearing has already failed in adhesive wear. And now this bearing here is having to pick up the load of the two pistons that are running between these bearings and the two pistons that are running between these bearings. So it's effectively having too much load applied to it and can no longer keep an appreciable oil film between those surfaces. So it's starting to go to adhesive wear as well. So we start to see more polishing in these areas here. This is the early stages of adhesive wear, is the polishing of the surfaces, right? So when we start to polish, we're just starting to reach surface melting temperatures. Sometimes that heat is pulled away through conduction into the body of the part, or that heat is pulled away via lubricant films or lubricating oil that's flowing through there. So when we see the polishing, it's an indication of adhesive wear or possibly two-body abrasive wear. Keep in mind that the two-body abrasive wear, if we don't provide a lubricant film relatively quickly, it progresses to adhesive wear like we see here pretty quick.
Yeah.
Okay. So
Are
any questions,
all
James?
those bearings, all of those came out of the same engine?
They did. This was the number one main bearing, two, three, four, five, six, and seven.
Yeah.
Yeah, it's out of a this was actually out of a 12-cylinder engine. So I guess I might as well go ahead and give you the root cause of this failure here.
Yeah.
It was actually since we talked about contamination a good bit last week and abrasive wear, it was actually what we would consider a dirty build, meaning that there were a lot of abrasive contaminants left in the suction screen. There were abrasive contaminants on the back side of these bearings which is an indication that there was dirt present in the caps when the bearings were installed,
Mm.
which also reduces the oil clearance because we're pushing that bearing up a little higher.
Hmm.
Okay. All right, so next one, we've got a couple of pistons here that have experienced the adhesive wear, and notice the melting and the smearing that you see, right? Surface temperatures are extremely high, and we're no longer able to keep a lubrication film between the piston and the cylinder wall. Oftentimes, this can happen when cooling systems overheat. If we get the pistons too hot and they expand too much, that clearance goes away, and we start to generate the adhesive wear as well. This piston on the left is a classic example of an engine that has been overheated, where the cooling system overheated and the piston itself actually starts to seize or generate adhesive wear on these areas here of the skirt. Can you see my cursor going
Hmm.
up and down?
Yeah.
Yeah, so it'll happen in those places on either side of the skirt, and we refer to this as 4-point seizure. And then as it progresses, the adhesive wear will progress all the way across the skirt, like we see in this case here. And the problem that this creates is not only are we dropping this aluminum into the pan and it can flow through the lubrication system, some of it gets past the filter, it does bearing damage and other damage. But as you can see on this 3600 piston, as these aluminum pieces come off, they start to get up into the ring assembly here. So this is our what we refer to as our gross oil control ring. That ring is stuck effectively
Hmm.
because of this debris, so we can no longer control oil. So now it starts to get up past this ring here, which is our fine oil control ring, and up into the compression ring, which means we start to potentially burn oil in the combustion chamber, which is that's no bueno. We don't want to do that. Oil consumption problems, catalytic or catalyst plugging problems, emission related issues, as well as excessive amounts of heat and potential catastrophic failure. So when we talk about potential catastrophic failure, if we look at this piston here, what that can progress to, Michael, is as this is seizing in the bore and the heat perpetuates, it just continues to build, the piston's getting larger and larger, that it actually begins to pull itself apart. So the skirt sticks in the bore, and the connecting rod is still trying to push the piston up and down. So it basically tries to pull the connecting rod away from the piston via these areas here, because
Uh,
the wrist pin is running through this area here over into this area here. As this sticks and the crank's still pushing that connecting rod up and down, it rips the piston apart. So this is fairly catastrophic on a 3600 piston,
I would say so.
what we're
Now,
seeing here.
now you mentioned aluminum. Those look like cast? Are they aluminum?
So in this case here, they are an aluminum skirt.
Yeah.
In other applications, such as, need to be careful how I say this, but on the dirty diesel side of things, um, oftentimes we'll see steel pistons used as well.
Yeah.
And I do have an example of what we see with the steel pistons because it looks a good bit different. So let me back up a couple of slides here.
What do cylinders look like that you pull those pistons out of? I
So
mean, does it
effectively,
totally just, I mean, does it look like the same as that piston?
it does. The cylinder
Yeah.
walls will look like this. If we have the initial 4-point seizure, and this is a good tip for the listeners, is anytime that we pull a cylinder head off of an engine, if we pull a cylinder head off of an engine, it's always a good idea to roll every piston down to bottom dead center of its stroke and inspect the cylinder walls. You can't see the skirt. All you can see is the crown of the piston. So we inspect the cylinder walls for this 4-point seizure. And when we see that, that's a pretty strong indication that that piston needs to come out and the piston and cylinder liner need to be replaced, as well as the cause of the adhesive wear needs to be investigated.
Hmm.
Okay, so when you talked about the inside of the cylinder wall, here we've taken a cylinder liner and we cut it in two and then photographed it, but this actually uses a steel piston rather than an aluminum piston. So this piston here is all steel, and the black stuff that you see on here is what's referred to as an anti-friction coating or a moly disulfide coating. that should be on the whole piston skirt area. But as this piston experienced, or this cylinder experienced its problem, then we started to generate adhesive wear. So we see the smearing and the very irregular or feathered edges of the adhesive wear. It's worn most of the moly disulfide coating off. But since this has a bit of a higher melting temperature than the cylinder liner, what we see is that we're just generating tempering colors because of the heat that's generated. We're really not seeing this material melt and adhere to here, or this material melt and adhere to here, right? So we're just seeing a lot of frictional heat. Can you see the blues and the blacks, and
Oh
and
yeah.
there's some gold in there as well. So as a just kind of a general rule of thumb, Michael, when we talk about things like tempering colors, like we see here on the cylinder liner, the gold colors start somewhere around 400 to 450 degrees. The blue colors occur somewhere in the range of 600 to 900 degrees, where usually the grays around 1,000, and then 1,200 degrees and up, everything tends to be black.
What
So
is the
these are good.
normal, what's the normal operating temperature?
Oh, in this case here, well,
Hmm.
this component should be running fairly close, maybe actual surface temperature just a little bit above engine oil temperature.
Hmm.
So your engine oil temperature on these engines, talking with a lot of guys in the industry, they don't typically see in gas compression above 200 degrees Fahrenheit
Yeah.
of the oil temperature. Now the piston crown temperatures can get significantly warmer, but we're also shooting oil at the bottom of that crown, helping to keep it cool.
Hmm.
Okay, so when we talk about those tempering colors, those are good indications of how hot something got, and that's factual data, right? If we see something starting to turn gold, well, we know it's been 400, 450 degrees. We're starting to see the blues and the purples and stuff like that, then we know we're somewhere 600 to 900 degrees. And the way that I like to think of that, Michael, is what are lubricants doing at those temperatures? And the reality is that at 400 to 450 degrees, the lubricants are extremely thin. Some lubricants are possibly reaching their smoke point. At 600 to 900 degrees, the oil is starting to carbonize. So now we're just generating carbon, and the lubricant film is evaporating essentially.
Yeah.
Okay. Any questions on this one?
No, that's pretty self-explanatory.
Okay. Okay. All right.
Got your
Um,
color coded temperature guide. I like that.
exactly. Yeah. And that's something that we teach in our classes as well, as part of our metallurgy module, because also, you're familiar with heat treating of parts.
Yeah.
Yeah, so when we see those temper colors and a part has been hardened and tempered, and if it's been tempered at 350 or 375 degrees and we see that it's turned blue, we've effectively hurt that heat treat of that
Yeah.
part because we've over tempered or softened it. Here's another example of a 3600 piston that's just experienced excessive amounts of adhesive wear. And this one hasn't gotten to the point where it's starting to seize the rings, but it's definitely making secondary debris and wreaking havoc on other areas of the engine. So let's see here. Here we've got a crosshead bushing out of, I believe this was out of an aerial compressor.
Hmm.
And this crosshead bushing is a bronze material. So we can see again the tempering colors and the smearing. I think I've got a little bit closer up of that. There you can see it. See all the
Yeah.
feathered edges, the
Hmm.
irregular edges, the carbonized oil deposits, and the smearing. So again, we definitely have a lubrication related issue in this case. What tells us that it's probably a lubrication related issue is that damage is all the way across the bearing. If that damage were just in this area here of the bearing, then we might consider a potential alignment issue. All right. So here we've got some compressor bearings that have also been wiped, or extreme amounts of adhesive wear. I think last week we saw some examples of some bearings that weren't as heavily damaged, right?
Uh-huh.
So several things can cause this. We we see all sorts of different issues related to crankshaft surface finish, um, clearance issues, alignment issues. soft foot issues that are causing alignment issues or potential deflection of the frame or case or of the engine block in an engine that tend to reduce clearances and apply load unevenly across a bearing, or just the fact that we don't have lubricant present or the lubricant has been contaminated. So keep it in mind when we say that the lubricant is contaminated, we're not just talking about abrasive contaminants. If we have a water pump failure or an oil cooler failure and we contaminate that lubricant with coolant or with water, well, the lubricant or the water are only designed to, or excuse me, the coolant or the water are only designed to lubricate one thing in the engine, and that's the seal in the water pump. It doesn't work real well when we start mixing it with lubricating oil.
What is that thing on the left? It looks like a nail sticking out of it. Is that just a
This here,
yeah? Is that
so
just a
this
piece
is
of metal?
yeah, so these bearings, I think we covered bearings in the first podcast or the second podcast we did, but these bearings have multiple potential layers of materials, often starting with a steel back
Mm-hmm.
and then an aluminum layer bonded to the steel back, and sometimes a copper or a nickel bonding or diffusion layer on top of that. And then oftentimes a Babbitt or something like an LTO or a lead tin copper overlay on the top of that surface, and then sometimes a tin flash coating on top of that. So we have the potential of multiple materials that have different melting temperatures. The aluminum or the lead tin both have relatively low melting temperatures, where the copper has a bit of a higher melting temperature. So as that lead tin or the aluminum starts to melt, it starts to pull off. The crankshaft, because of the adhesive wear, is actually adhering to the crankshaft and it's pulling this material off.
So that's just
That's gonna,
material being stripped off.
it is. And let me see, I might have a picture here where we can see that a bunch of this material has been pulled off. And we can see that material building up in this area here.
Oh yeah.
So keep in mind that when we take a close look at this, this is my oiling groove and my oil hole. So oil gets delivered through here and through this groove. And here we can see where the material, the layers are peeling off,
Mm-hmm.
right? Everything is real dark and black. So that's a pretty strong indication that I probably don't have any lubrication present. Oftentimes when we spin bearings and they don't get black like this, they're spinning for another reason. We could still generate adhesive wear with oil present. It just keeps the temperatures a lot cooler. So we tend not to generate those tempering colors because the temperatures have kept much lower, because the lubricant is acting as a coolant more so than a lubricant at that point, if that makes sense.
Mm-hmm.
Okay. So here we can see this crankshaft that this bearing was riding against, and it looks like we had a little bit heavier load on this side here, maybe than this side here, just judging by the damage and the coloration. But we've had no contact in the center because that's where our oiling groove is in our bearing. But you can still see the debris that's pulled off of the bearing, right?
Mm-hmm.
Collecting in these areas here. And we're starting to generate some considerable thrusting, and you can see the temper colors in the crankshaft counterweight as well.
Now is this a clearance issue because it doesn't go all the way across and you've got kind of got that selected however many inches that is of really clear wear?
So in this case here, it was an alignment issue that they experienced on this machine.
Mm-hmm.
And if I'm not mistaken, they did run into a soft foot issue due to a fastener failure, and then the frame assembly being able to essentially twist because
Mm-hmm.
it's not bolted down. So it starts to twist and it puts this bore out of alignment that the crankshaft rides in. So that's there's a little bit closer up for you. You can see some of the debris here. We can see again those feathered edges and the tempering colors and the bearing material adhered to the crankshaft. We see the same thing on this side, just not quite as severe. So
Mm-hmm.
probably less load in this area here, more load in this area here. When
Now
we do
is
see
that
this,
debris that's on there? Is that kind of welded on there because of the
this stuff
heat?
here,
Yeah.
it's actually not. This
Oh.
is not. This is, but this is not because it's in that oiling groove.
Hmm.
One thing to note though is as this is generating high temperatures, Michael, we can see that we've still got oil flow coming in here. And that oil, since this is getting hot and the oil is cool in this area here, it's starting to cause a series of small surface cracks. Can you see
Hmm.
those cracks here?
Yeah.
Yeah, so almost like quenching that area because it's getting hot and we're hitting it with cool oil and it's expanding rapidly, cooling quickly, expanding rapidly, cooling quickly, and causing all these cracks, which are fairly common to see. So one thing to note is that when we see this, this isn't something that we'll typically just buff out with some emery cloth and put a new bearing in it. I got to tell you, it happens, right? So it's just so guys understand that at this point here, a few things have happened to that crankshaft because of the heat that's and load that's been generated and excessive clearances. The crankshaft is most likely bent. The crankshaft also most likely has taper wear on it now because we've taken steel material off as well as bonded bearing material to it, and the surface finish is extremely rough where it needs to be extremely smooth if we're going to put it against a new bearing.
Mm.
So just a few tips there. I think that's it for the presentation. So I'll go ahead and stop sharing that.
Man, that was great.
I hope that helps a little bit and gives people a different perspective to look at things when they start to fail and when they have lubrication related issues. But when we talk about adhesive wear, kind of a checklist, let's start with oil level. Where's the oil level at? And keep in mind that oil level being too high can be just as bad as being too low
Now,
because
why
oil
is
level
that?
it starts to generate a tremendous amount of heat. All of these rotating parts are sloshing through that lubricating oil, generating frictional heat. That sloshing also tends to aerate the oil. And as we aerate the oil, we effectively insulate it. So now, as the oil is flowing through the oil cooler, we can't conduct the heat from the fluid to the tubes in the cooler because of the air bubbles insulating it. So we tend to see excessive operating temperatures when we're overfull as well as underfull. And underfull can cause all sorts of different issues as well. Um, Two-body abrasive wear progressing to adhesive wear very, very quickly. So oil levels, part clearances as well, surface finishes, again, cleanliness of assembly, meaning that if we've got debris behind the bearing when we install it, then we're going to effectively reduce the oil clearance between the bearing and the crankshaft. If we have debris on top of the bearing when we install it, then the crankshaft is going to smush that into the bearing, and that's going to raise more material and potentially start to scratch the crank. Anytime that we're scratching steel like that, we're generating heat, right?
Hmm.
So that causes that bearing joint to run hotter as well. Just some things to think about.
Oil levels, clearances, and finishes.
Yes, sir. Maintenance practices as well. So the longer we run our oil, the thicker it gets when it's cold, the thinner it gets when it's at operating temperature. So we end up with thinner oil films. So maintenance practices are paramount, obviously. And I think that'll about do it. I'm sure I'm missing something in there, but that should
No,
give
that's
it.
that's four good things to take away.
Okay, good deal. And we're always happy to help out. We tell our customers, the folks that take our training classes, that hey, if you want to use this as a resource, shoot me some pictures. Be sure that they're in focus and clear. But if you want to shoot me some pictures, I'm happy to tell you what I see or pose some questions that'll get you looking a little bit deeper. If you're going to need me to produce a report or something like that, well, then I'm going to need a purchase order.
Yeah.
But kind of how that works. But
How
as
often,
a
how
resource
often
to
are,
the industry,
yeah,
we
how
like to
often are
help
you
out.
getting texts and emails about pictures like, man, we had a crash and here's the pictures. How often does that happen?
So it's hit and miss, but fairly frequently,
Yeah.
several times a month,
Yeah.
on the gas compression side, and then including all of the different market segments that we serve. It's something literally every day.
Yeah.
Yeah. So
All right. Well, that was a really quick and visual representation. I appreciate you putting that slideshow together. That was great.
I hope that helps. Um, any other questions that you might have, or anything else that you want to cover in regards
No,
to?
no, I wrote down several things, but you answered them as you were going along. I was going to ask you a question, but then you would kind of go in and explain it further. So, no, I really don't. I think this is a great resource for folks out there when they're doing detective work and looking at what went wrong. Those are great pictures and great information to have to be able to take the next step on what they need to do differently.
Excellent. As another potential resource, you mentioned what went wrong. So if the
Oh,
listeners
yes,
look at if they don't subscribe to Gas Compression Magazine, I recommend that they do. It's a free subscription. You can get a paper copy delivered to your house or read it online with a digital copy. But for the last several months, I've been helping out with a column in that magazine. And that's the name of the column, What Went Wrong.
that's right.
So I'm actually following up our last gas compression podcast with the February article will be on abrasive wear,
Oh, great.
and looking to just kind of pair the series together so people have more resources in the industry, right?
That's great. Not second that. Brent Haight and the guys at Gas Compression Magazine do a phenomenal job. It's like I don't really get any magazines delivered to my house, but when I get the Gas Compression Magazine, I enjoy it, and I look at it online too. So yeah, if you're listening to this and you're in the industry and you don't get the Gas Compression Magazine, just go to their website and just get it signed up. It's free and it's really great. Those guys, Brent and those guys do a great job.
They absolutely do. It's a great publication and another good resource.
Yeah. All right. So what are we talking about next week?
Next week, we're going to cover corrosion.
Okay.
So corrosive wear.
All right. Well, looking forward to it, Jim. As always, you do a stellar job of presenting the material and explaining it in layman's terms. So thanks for doing that and look forward to seeing you next week.
All right, Michael, thank you.